Morning, everyone. Today we're going to discuss units of radiation, radioactivity. Some we've already covered a little superficially, but we're going to get a little more in depth through this lesson. The units we're going to cover really are activity. So that's the quantity of radioactivity that's present, say, in a source, in a patient, anything that is radioactive. And then the varying ways that you actually quantify the radiation coming off of that source, and how you then quantify the radiation that is absorbed in something, most commonly another person's, a body tissue, something that you're trying to quantify. So this little chart does this graphic does a pretty good job of showing the differences of the different units and functions that they serve. So if you think about it, you have a radioactive source. There's some activity there. That activity is from the decays of the source. They're giving off radiation, whether that's particle radiation or photon radiation. Some of that radiation interacts with the air. It ionizes the air. That gives you an exposure. Some of that radiation interacts with matter that is around. That could be a person, that could be a patient, that could be a research animal. So there is some absorbed dose. When that absorbed dose is a person, then we are further seeking to sort of quantify the biological effect that comes from an absorbed dose. And that's where you get into some subtleties of, okay, which tissue actually absorbed this dose? What type of radiation was it? And that's how you go from this physical quantity of absorbed dose to what we will discuss as the varying definitions of dose equivalence. And you'll see that unit is the rem or the sievert, and that has a lot of significance in health physics. Okay, so just a refresher on really mathematical units in general, scientific units. There's a number of prefixes that sort of modify the unit you're talking about. You don't really need to know all these, but some of the main ones being micro, milli, you hear microcuries, millicuries, very common. Nanocuries, less so. Once you get down to picocuries, you're talking about really individual decays. So that's in real world settings, that's not something you're going to use very often. On the other end of the spectrum, when you're talking about activities in SI units, it's very common to have megabecquerels or gigabecquerels. So really, you should have some idea of what these signify in terms of the modifiers. Now, we also have the unfortunate task of dealing with classical US units versus SI units. The SI units are the dominant unit in the world, and they are slowly replacing the US units, even in the US. But for the time being, we unfortunately have to be fluent in both of them because it's not uncommon to hear an SI unit versus US unit. Sometimes you only hear the SI unit and you have to be sort of on the fly able to understand what that signifies. And then, just when you're dealing with the same units, just with the modifiers, also just understanding exactly what that signifies. So this is a review of what we covered. Varying isotopes. Every element on the periodic table has some radioactive isotope. There's a few of them that don't for the most part. Most of them have lots of radioactive isotopes. Only a certain number are used in the medical field just because of their half-life, because of their decay characteristics. A review on radioactive decay. It's important to remember that you don't actually undergo a true decay until there is some sort of rearrangement of the nucleus. That's generally from an emitted charged particle, whether that's an alpha coming out of the nucleus, or that's an electron coming out of the nucleus as a beta particle, or a positron. So that it fundamentally changes the atom versus an unstable atom giving off, say, just a photon or an X-ray or something. That changes the energy state of the atom, but it doesn't fundamentally change the atom there. It doesn't change one element to another element. It just changes the energy state of the same element. So you need to have that particle emission or that particle absorption in order to truly have a radioactive decay. And half-life we covered very extensively so far. We're just going to get into it a little bit more. It's the amount of time it takes for a certain activity to decrease half that activity. If you track it over enough decays, you see it has that logarithmic curve that starts to approach zero but never actually hits zero. We mentioned effective half-life already, so I'm just going to touch on this real quick. You have that physical half-life. That is a set in stone law of nature. It's not modified by anything we can do, anything we know at the moment to do. But then as soon as you put any sort of radioisotope into a biological system, there's going to be some degree of removal from the body. The example I often use, probably have already used to you guys, is a radioactive iodine patient. These patients come to us with their thyroid surgically removed. The point of the iodine is to radio ablate any remaining cancerous thyroid tissue. So it's given into the body in a very large dose. But we know that in the first 24 to 48 hours, something like 99% or more of that radioactive iodine will be urinated out. So if we're concerned with the amount of radioactivity present in that patient, we don't want to go just by the physical half-life. Because if we give a patient 250 millicuries of iodine 131 and say, okay, well, this is only going to decay by half every 8 days, then we would think that this patient is going to be dangerously radioactive for weeks and weeks, or months or more. But we know that because of that very rapid biological removal, we're only going to be dealing with a small percentage of what was actually given as therapy a couple of days out. What does stick in that remaining residual thyroid tissue generally does start to decay with more closely to the physical decay. So that means that that is a situation where if that 1% or that 0.5% does stick, then that may be around for a while. And that's something that we have to take into account. But yeah, it's not so clean as one biological decay and one physical decay. The biological removal has some variations to it. Often you'll come up with what's known as a bi-exponential curve, which has essentially two curves that combine. So you have that very sharp drop off, and then what sticks tends to level out and decay more closely to the physical half-life. So when we talk about activity, remember we're not talking about the physical material present. We're talking about the activity of that physical material present. So that's where that half-life or that decay constant comes into play, because you can have a lot of material, but if it has a very, very, very long half-life, it's still not going to be very radioactive. But if you have a small amount of material with a very short half-life, it could still be very radioactive because what is there is decaying very rapidly. So I mentioned that divide between the US units and the SI units. Unfortunately for activity, it's tricky to go back and forth. The Curie is the original unit. It's named after Marie Curie. It's equal to about 1 gram of radium, the disintegrations of 1 gram of radium. So there's about 2.22 times 10 to the 12 disintegrations per minute. So that's a very high activity. That's why very often you'll hear millicurie or microcurie, and you can see that the exponent is modified to reflect the lesser number. It was replaced by the becquerel. It was supposed to be replaced everywhere by the becquerel, sometime in the 80s, and only now is it starting to actually happen, really. But the becquerel is 1 disintegration per second. So you see the transformation from Curie to becquerel. The conversion is not a very clean conversion. Fortunately, for the most part, we will just be dealing primarily with curies, millicuries, microcuries in this class. I mentioned that the activity is not directly related to it is directly related to the number of atoms, but the big modifier is that decay constant. Remember that the decay constant is equal to the natural log of 2 over the half-life, so that's where the half-life comes into play. Really, the decay constant is the fraction of the atoms that will decay over a certain time period. So that's why this decay constant is in the unit of inverse time. So you'll have per second, per minute, per hour. It could be any time that you choose as long as you do the correct conversion. But it will say really the fraction of atoms that will decay per the time period that you initiate. So if you have something with a very long half-life, the decay constant will be very, very small, because over a certain period of time, over a minute, something that has a million-year half-life, not much is going to decay in a minute. So you'll have a very, very small decay constant. But if you have something that has a much shorter half-life, you'll have a larger decay constant. But really, that is what links the number of atoms to the activity of a sample. And we'll go through one of these problems to further show really what this apparently simple equation really means, because it's important to understand from, you know, an actual physical activity standpoint. So that's the quantity of radioactive material that could potentially be giving off some sort of radiation. Everything past this point is going to be an effort to quantify the radiation from that source. So there's a number of different ways that we quantify that. Some out of necessity, some out of convenience, and some in between. But really, one of the first ways that was developed to measure radiation, for a while there was really no good way to quantify radiation, and that's where this erythema dose came from. It's really how long until my skin starts to get burned by this radiation. And so that is not the best unit, obviously. Soon there were some exposure rate meters that started to appear. These were able to sort of quantify the ionization happening in air. It's important to note that exposure only applies to photon radiation. So you would not use an exposure unit for beta radiation, for alpha radiation. It's really just the number, you know, the sum of the charges being produced by this ionizing radiation traveling through air. So the unit of exposure is given as the Rankine. You know, just going back to Wilhelm Rankine. The SI unit is the Coulomb per kilogram of air. So this really is just the energy produced in the air by this radiation, you know, ionizing and essentially giving energy to the air ions that are created. It's not really used outside of instrumentation these days. So it is important from an instrumentation standpoint, but it's really not, it doesn't have any basis in terms of potential biological effect to somebody. It does, but it's indirect. It's not used in that form anymore. So radiation that is not in air is really what we're concerned about. We're concerned about radiation in a biological system, in human tissue. So that's where you need another unit to quantify this, because that exposure, one exposure scenario doesn't always lead to the same absorbed dose scenario. So there's differing factors that come into play. And that's why we have a different unit for absorbed dose. Now, absorbed dose traditionally was the RAD, the Rankine absorbed dose, the SI unit being the gray. Because different materials are made up of different elements, different atoms, they're not going to absorb the same exposure the same way. So the RAD is defined as 100 ergs per gram, thrown in another unit there. Ergs are, again, like a holdover unit. They're a unit of energy, but they, for the most part, you really don't use ergs outside of defining the RAD. You'll see that 1R, so one Rankine of exposure, can equal different absorbed doses depending on what you're going. 1R equals, you know, a certain number of rad in air. It's about 0.887 rad in air, but 1R in tissue will equal pretty much 1 rad. You know, fortunately, it's very close to the point where it's you really can say that 1 MR equals 1 millirad. It's close enough, but it's important to understand that it's not exact. It's not a clean transition like some other things. And a gray is just 100 rad, so it's a larger unit. A gray which is equal to 1 joule per kilogram. I guess, again, if we're going by pure SI units. Joule just being energy. You know, joule is a large amount of energy. It's more commonly used for, you know, non-subatomic physics. So you talk about joules when you're talking about, you know, electricity and magnetism, things of that nature, less so with some atomic particles. However, the joule per kilogram being 1 gray, when you're talking about, you know, treatment doses from a linear accelerator, you do tend to start to approach those energies. It's less so from a radiation safety standpoint where you're dealing with lower doses. So, okay, just to recap up to this point, you have a source that is giving off radiation. That radiation ionizes the air to a certain degree. So if you have a meter that is in that air, you can detect the level of exposure. And knowing what sort of materials might be exposed to that exposure, you can then start to make assumptions about the absorbed dose, because it's not so easy to just actually just measure the absorbed dose inside somebody, because how do you get the correct detector in there? You can put detectors inside of phantoms that imitate the human body, and that is one way that is used very commonly. But for convenience, there's nothing easier than picking up an exposure rate meter and characterizing a radiation field based on its ionization of the air. That is something we do for all of our surveys. That's something we do for patient surveys. That is our main method of quantifying radiation. Then you have the absorbed dose, that is really just the radiation that is absorbed into matter, into a body, into shielding. Taking it one step further, there is what's known as dose equivalence. So for this, you'll notice that there is a different unit. This is in rem, not rad, not Rankins. So anytime you see rem or sievert, it's important to understand that this is not an actual physical quantity. This is taking that physical quantity of absorbed dose, something that is just energy per unit mass, something that can be directly measured, and you are applying it to you're trying to give a risk factor associated with that absorbed dose. So when you're talking about risk, you're talking about, a human exposed to this radiation. So you have to factor in the different types of matter that make up a human. You have to factor in how different types of radiation interact with human tissue. And so when you talk about the different types of radiation, that's where you get something called a radiation weighting factor. It used to be called a quality factor, but now it is a radiation weighting factor. So what that radiation weighting factor does is it takes your absorbed dose, you times it by that radiation weighting factor, and that gives you number of rem or number of millirem. And that is the relevant radiation safety unit that we're looking at. That is what our dose limits are in. That is what our dosimeters are measuring. So that's the unit that we want to understand from a radiation safety standpoint. So I mentioned the radiation weighting factors or quality factors, and you'll see that for photon radiation, beta radiation, it's pretty much 1. There is some variation to that, but it varies around 1. So for ease, you can just use 1. But then we talk about alpha particles. I had mentioned that alpha radiation is comparatively more biologically damaging. If we go back to that background lesson, we look at radon. Radon is an alpha emitter. So that is why it gives such a large dose. That is why it's such a large percentage of your natural background radiation exposure, is because it has all these alphas that are irradiating your body. Neutrons of unknown energy are given a weighting factor of 10. If you do happen to know the spectrum of neutron energies that you're dealing with, some neutrons have a factor up to 20, and some of them go down to 1 or 5, depending on which advisory body you're using. There are different quality factors depending on if you go by the international numbers or the national numbers. They are closely related, but they don't have the exact same number. And then you have protons, also have a higher quality factor than 1. Okay, so I mentioned that the photons, X-rays, gamma rays are 1, but even that is not perfectly true. You'll see that with the 1 being here, that conversion from Rankine to rem and rem to Rankine, you'll see that 1, it kind of trends around 1, but when you're dealing with the very low energy range, or low energy through the high energy, you see this sort of characteristic spike that starts to level out around 1. But it's important, if you're looking for very accurate measurements, that you take into account what photon energy you're dealing with and use the modifying factor for that. So that brings us to our dose limits. This is what your dosimeter is measuring against. This is what we as a group are trying to keep all the employees below, because it is a big deal if someone goes above their regulatory limit. That signals that something is potentially very wrong with the health physics program. You notice that these are in the units of rem or sievert. Again, this is not a physical quantity. These are numbers that are sort of portraying some sort of a risk factor, which is what we want, because the whole concept of dose limits is to minimize the risk to a worker who is working around a hazardous substance, which in this case is the actual radiation. So these dose limits represent a level of acceptable risk to workers. And so not all dose equivalents are the same, depending on what type of dose you're trying to portray. You can often refer to the deep dose versus the shallow dose versus the lens of the eye dose. And these have different limits, as we saw here, because of just the understanding that certain areas in your body are more sensitive or less sensitive. So something like a shallow dose can be higher, or an organ dose can be higher than a whole body or deep dose. And that's why the limit is 10 times higher. So deep dose is generally measured at 1 centimeter of tissue depth. There's something called the mass thickness. We'll get into that a little bit more with shielding. It's a unit that doesn't really make sense. You don't use it by itself. You don't use it, in isolation. You use it in combination with density. Because if you look at the units, milligrams per centimeter squared, it doesn't really make sense that an area would have weight. But once you multiply this times the density of the material that you're dealing with, you suddenly get the units of inverse centimeters or inverse distance. And that is very useful for shielding. That gives you your linear attenuation coefficient, which starts to talk about how much photon radiation is attenuated by certain depths of shielding. But for our purposes now, for the time being, all you have to understand is that when you hear deep dose equivalent, that is the dose that is being measured at 1 centimeter depth of tissue. So if you think of radiation interacting with your body, some of it will just interact very superficially, especially if you have very low energy photons or particle radiation. They will interact superficially. Your skin will get a dose, but you will not get a very large, deep dose. Now, you would get an outsized shallow dose in that same exposure scenario, with the reverse being to that. If you're dealing with very high energy radiation, it's less likely to interact in a shallow manner, and your skin would get less dose compared to, again, a lower energy. But your shallow dose, this is that 50,000 millirem limit, or that 50 rem limit. So this is measured at a very superficial depth. So it's measured at 0.007 centimeters. So that's really what that represents is the depth of it takes to get to healthy living tissue. Your skin, it may be unpleasant to think about. Your skin is essentially covered in dead skin cells. It's sort of a shield for your body to protect you from, just from sun, from chemicals, really from anything. Your skin has a sort of protection mechanism, which is dead skin slowly leaving your body, slowly flaking off of your body. And so you have to count for the radiation that gets through that. And that would be measured at it's a very superficial depth, but it is some depth. And that would equate mostly with the dose to your skin. Now, lens of the eye is treated differently than every other organ because of the known risk of developing cataracts. So that has its own mass thickness. So it's measured at a little bit different depth. And it also has a different limit. So it's 15 rem as opposed to 50 rem for other organs. And it's also measured at a depth of 0.3 centimeters. So that represents just sensitive structures in the eye. So this just sums up the depths, the annual limit, and then the annual limit in SI units. So it's important if you know the conversion between these two units, then you only really have to memorize one limit. But it's important to memorize the depth that the dose is measured at and the millirem limit for those individual depths. Those are very important for you to know because those are definitely potential questions on any board exam and other exams that you may or may not be taking. Hint, hint. Tissue weighting factors. These are another sort of modifier of absorbed dose to, again, portray risk. So you're taking that physical quantity, that absorbed dose, which is just energy per unit mass, and it's another modifying factor when that absorbed dose is human tissue. So not every tissue is created equal when it comes to radiosensitivity. Some tissues are way more sensitive, and those are generally tissues that are unspecialized, that are rapidly dividing, they're highly metabolically active. Those are the tissues that are going to be most sensitive to radiation. So that's reproductive organs, blood cells. Those are the ones that get hit first and hardest by any exposure of radiation. The flip side is also true, actually, in that cells that don't have these characteristics are very radio resistant, and that's muscle tissue, nerve tissue. Those are the ones that are going to be least sensitive to radiation. So those tissue-weighting factors reflect that fact. Here, we'll go through. So these are some of the values here. Really, what you do with those tissue-weighting factors is, well, here, I'll go. So that tissue-weighting factor, generally, when you have a situation where only a specific organ is exposed, or there's a dominant organ that's exposed, you're most likely dealing with internal dose. You're dealing with some sort of radiopharmaceutical or some sort of just element, some sort of radioisotope that favors one organ or only a couple of organs. Again, I beat radioiodine to death, but that's a good example of that. If you ingest radioiodine, the dose of concern is to your thyroid. So you would take that dose to your thyroid, which would what would be known as the committed dose equivalent. So that dose to your thyroid is, we're only looking at the dose to a specific organ. That's what's called the CDE, or the committed dose equivalent. You can come up with activity in the certain organ. We do have thyroid bioassays, which attempts to quantify the amount of radioactive material that might be in a thyroid after an accidental exposure scenario. And then from that measurement, we can then assign a dose to that organ. So then we'll know the dose that's given to that thyroid. We can compare it against the organ dose limit, which is at 50 rem. What we can also do is multiply that organ dose by the weighting factor for a thyroid, which we'll see here. Thyroid went from 0.03 to 0.05. So, they reevaluate these factors. And if something shows that it is more sensitive, more prone to both just biological damage and potential cancer risk, that reflects a higher weighting factor. So the thyroid, it's kind of middle of the road, but you would take that dose to the thyroid and multiply it by that 0.05, and that would give you the contribution to a whole body dose from that thyroid dose. So the thought being that if you have a radiopharmaceutical circulating the body, you will have known doses to each of these organs, and you take those known doses to the organ. Say if it favors the thyroid, or some radiopharmaceuticals are non-water soluble, so they leave primarily through the GI system. So the colon will get a large dose, stomach, everything in the GI tract will get a large dose, and then you'll have to use these weighting factors to multiply those doses individually. But you'll see that this sums up to 1. So essentially what that means is that you take all those individual organ doses, times them by the respected weighting factor, and then that sum gives you that whole body dose. And that whole body dose is that whole body internal dose is what's known as committed effective dose equivalent. So I like to think of the committed, like as soon as you ingest one of these things, whether it's on purpose or by accident, you are sort of committed to that dose. There's no way to then easily take it out of your body. So you are committed to that dose until it leaves your body or decays. And so that is what the committed dose equivalent is for an individual organ, or when you times by the weighting factor to get to the whole body dose. Now, when you talk about the total organ dose, remember that committed dose is for internal exposure. You may also have some external exposure that, for the most part, irradiates your body a little more uniformly than something kind of moving around inside of your body. So your total organ dose equivalent would be that committed dose equivalent of the organ times the actual deep dose you get, which is generally whatever your dosimeter reading is. Your dosimeter is measuring external radiation. So that DDE, that deep dose equivalent, is essentially what your badge is reading. So if you take what the internal exposure to the specific organ times it by that external exposure that hits your entire body, you can get the total organ dose equivalent. This would be what would be compared against that 50 rem limit. Now, total effective dose equivalent, this is what takes into account the sum of all the internal exposures to the organs plus that external exposure. So this is the individual organ doses times their respective weighting factors, all summed up, and then you add that to your deep dose equivalent, and that is what is your total effective dose equivalent. That is what is referenced when you see those annual limits. So this is essentially, you have your dosimeter. That's your deep dose record. That's what we get when we return dosimeters and get them read. Really, the only internal doses that we add to those are for situations where we know someone was exposed and we have a reliable way to quantify that dose. Usually that's thyroid exposure, or that's iodine exposure, that we can then measure the thyroid and assign a dose. And when we do get a certain dose above a certain threshold, we will add the committed effective dose equivalent and the committed dose equivalent of this thyroid specifically to someone's dose record, because that is a significant exposure that needs to be counted against your annual limits. So this just summarizes all the different doses we're talking about. I think that's the end of the presentation. We'll run through them one more time. We're gonna discuss them in person as well, because they're very important. But you have that total effective dose equivalent. That effective means that it's your whole body. It's not just an individual organ. That total effective dose, and then equivalent also means that you're factoring in the type of radiation. But really, that is just the sum of your deep dose equivalent times all of the committed dose from any organ that may be irradiated in a specific exposure scenario. If you're looking at just an individual organ, that's your total organ dose equivalent. That's that deep dose, which is thought to affect every organ uniformly, times the specific committed dose to that organ, which would be that dose times any sort of quality factor or radiation weighting factor. Yeah, the committed effective dose equivalent is just the sum of the organ dose times the organ weighting factor. And then one last thing to cover is that the ALI, you'll often hear the ALI talked about. That's your annual limit on intake. So this is sort of a value that does the work for you. These are values that are given to you by regulators. The ALI says that the certain activity that will lead to the limits, whether it's whole body 5 rem limit or the individual organ 50 rem limit. Again, referencing radioiodine, it's the best one to explain organ dose, is that you'll see an ALI for something like I-131. It'll be very low activity, because if you ingest a certain activity of I-131, you will very quickly hit your 50 rem dose limit of your thyroid. So it'll say, I think it's 30 microcuries. If the average person ingests 30 microcuries, they will get a dose of 50 rem to their thyroid. So the ALI is useful from our standpoint of, say we have a nurse that, handled radioactive urine and didn't realize she got it all over herself. So some of that iodine absorbed into her body. We take a bioassay measurement, or we take a couple of measurements, and we conclude that she ingested, or she had absorbed 5 microcuries of iodine-131. Well, we know the limit for 50 rem to the thyroid is 30. So that 5 is 1/6 of 30. So we can divide this by, or multiply by 1/6, and that would get you a little under 10 rem to the thyroid. So these ALIs are useful when you know how much material someone may have accidentally ingested or inhaled, or some other route it got into their body. So that's where the ALIs come into play. We'll touch on this a little bit more when we meet in person as well. But it's a lot of information on dose, but this is very important because this deals very closely to your dosimeter readings and the regulations that say, our dose limits for occupational exposure. So, there's a lot of information there. Just retain any questions, and we'll hopefully be able to clarify it in person. See you guys tomorrow. Bye.